Okay, if you don't have anything to talk about other than the course material, I'll start the lectures then. Okay, first I'll talk about some basic concepts um, in fluid mechanics. Hydrodynamics is a fluid mechanics basically, but for water. Okay, so we'll go through some basic concepts of fluid mechanics first. So what is a fluid? Okay. So a fluid is a substance that deforms continuously by when acted on by a stress. No, not just stress. Shearing stress. So here, shearing stress means the tangential force divided by area. That's what I mean by shearing stress. So if you apply the tangential force, and then fluid starts to move, okay, of arbitrary magnitude. So this is a very formal definition of fluid, and so when you apply some tangential shearing stress or tangential force, then the fluid starts to move. Here I said arbitrary magnitude, meaning that the magnitude doesn't have to be very large. Any small this force, the fluid is supposed to move. Okay. If you think of solid, and if you don't push hard enough, solid doesn't move, right? There is a friction, and you have to push a certain critical the force beyond certain critical force, then the rigid starts to move. Okay. But fluid, no matter how small the force that you apply, the fluid is supposed to move. That's the biggest difference between the fluid and the solid. So that's the definition of fluid, and fluid mechanics is, of course, the mechanics. Of course, describe as the behavior of fluids. So we want to describe the behavior of fluid, which might be at rest or in motion. So fluid doesn't have to be moved, doesn't have to move. Could be in rest and also in motion, right? And so if we are talking about the fluid which is at rest, then it's a fluid statics. And if we are talking about fluid which is in motion or which moves, then it's a fluid dynamics. But we are interested in fluid dynamics instead of fluid statics, okay, in this course. So if you have the water in a tank, and if water doesn't move, then we are talking about fluid statics. Okay? And if you talk about the pressure at the the side of tank, that's there is a pressure even though fluid is not moving, right? And then we are talking about fluid statics. So buoyancy is typically the fluid statics. But in this course, we assume fluid is moving, or in the ocean, we have waves, and then definitely fluids are moving, and therefore we are interested in fluid dynamics instead of fluid statics. Okay. So now we know when we apply force, fluid starts to move, and we want to know the behavior of fluid. What kind of behaviors we are interested in? We are interested in so the fluid characteristics of interest. Rest could be the velocity and the acceleration. Of course, we want to know the force, so stress and density and so on, and pressure if you want. It's part of stress as well. Okay. So we are trying to describe those the fluid characteristics through the by studying fluid mechanics. Okay. And so we have to describe those the behavior more in mathematical terms. To do that, what we typically do is continuum assumption. So of course the fluid consists of many molecules, but they are too small for us, so we are not interested in the molecular structures when we talk about fluid mechanics. Instead, we take some average of physical quantities over a small volume, and then we define velocity and acceleration and so on at that point where the small volume is located. Okay. So continuum assumption means we although there is a little space between molecules, but it's so small. Okay. We are interested in much larger scale the phenomenon, and therefore we assume there is no space between molecules and everything is continuous. Okay. And that's what the continuum assumption is. So under this continuum assumption, what we do is we characterize the behavior of fluid by considering the average average value of a quantity of interest in a small volume. So in other words, we are interested in macroscopic, description instead of microscopic, description. Okay. So if you really look at, molecules of fluid, and each has, the different velocity and acceleration, right? But what we do is we take a little small volume, which is, I really zoomed in, okay? And then we take an average over this. And then we'll say, okay, that is, the velocity or acceleration of this, volume. But when I looked at, if I'm a little away from that, it looks like, dot to me. And then it's, the acceleration and velocity at a point. Okay. And quite often we use, term dimension. So throughout this course, I will say, many times, about the dimension of some physical quantity. And dimension is important because, with many fluid characteristics, can be represented qualitatively. Okay. In terms of a length, L, time T, and mass M. So for example, velocity has a dimension of length divided by time. Okay. The unit can be meter per second, centimeter per second, miles per hour. But the dimension has to be, the length divided by time. Okay. And also the acceleration, for example, has a dimension of, I'll put, dot above, the equal sign, meaning that the dimension of, this acceleration is, as you know, L divided by T squared, right? And, density, for example, is mass divided by volume, so L cubed. Also, later, when you find, later you will solve a equation to find, velocity, for example, okay? And at the end, you found something, and then you might want to check, the dimension of what you found has the right dimension. The dimension is whether that dimension is right or not. Okay. And if that is not right, then so you made a mistake somewhere, and so on. So this dimension is important. Also, when we measure the magnitude of some physical quantity, we often use the dimensions as well. Okay. All right. So this is quick the review of some of basic the concepts that we are going to use. So once again, let me summarize. When fluid is different from solid, because fluid moves even though you apply very infinitesimal small force. Okay, so easy to move, That's what I mean. And that's why, the equations are more complicated than what you typically see in solid mechanics. Okay. And there are two kinds of fluid mechanics fields. One is fluid statics, and the other is fluid dynamics. And we are interested in the motion of fluid. Therefore, this course is for fluid dynamics. Okay. And throughout this course, we will find the behavior of fluid. In particular, we are interested in the velocity and acceleration and density and so on. But for engineering applications, we are trying to find force and therefore stress. Okay. But to find this, you need the velocity, for example. Without that, you cannot find force acting on the fluid, the structures. Okay, although the fluid consists of many molecules, we are not interested in such a small, scale motions, and so we just take, we treat fluid as a continuum, and therefore, actually, what we do is we do the average. We take the average value. I mean, in this course, we are not really taking any average, okay? Because we are not interested in molecules. We already assume everything is continuous, so any quantity can be written in terms of as a function of the space and time, okay? So you wouldn't see the averaging, but the underlying the idea is that we already have taken the average over many molecules, okay? And the dimension, we discussed that. Okay. So next what I'm going to do is I will talk about fluid kinematics before I talk about fluid dynamics. So this is another quick review for fluid kinematics. So most important, the fluid quantity is velocity. Okay. So we in the three-dimensional space, x, y, and z. We use a right-handed rule, meaning that if I start with x, then the y has to here and z has to be here. Okay, so everything rotates in this way, in this way. Yeah. Okay, then I look at a fluid particle. Once again, this is a dot, but there are many molecules. We already have taken the average. Okay, so even though I say for a fluid particle, I'm not talking about each molecule, and I'm talking about the small real volume. Okay, to your eyes, it's a dot. Okay, all right. So let me give it a name of this particle A, and then there is a position of this guy. When I put underline, I am talking about a vector. Okay, so this is a vector. So meaning that when I put underline, I have a three component, right? That's what I mean by vector. And this guy, as I said, I'm interested in fluid motion. So this fluid particle moves in time. So at a certain time t, this guy is sitting here. Okay. So there is a position vector correct? And the later time, fluid particle moves, so goes somewhere else. But I'm still looking at the same fluid particle whose name is A. But this is a position at different time, let's say t plus delta t. Once again, this is the position vector. So fluid particle is moving from this position to this position. Okay. So since fluid moves, definitely fluid particle has a velocity. If fluid particle doesn't have a velocity, then fluid particle wouldn't move, right? Velocity 0 means fluid particle is not moving at all. But since particle is moving, the fluid has a velocity. And also, of course, there are many fluid particles in space, so I can pick another point. B, and this guy has the position vector xb at a given time, and this guy will move somewhere else here at a later time. Okay, so each fluid particle is moving, as it it is supposed to. And this solid line represents the position of fluid particle A at different time. Okay, so this guy is continuously moving, and this solid line is called path line. So I say this is a path line of fluid particle A. This black line is path line of fluid particle B. Okay, so this line represents the real trajectory of each fluid particle. Now, there are two different descriptions in fluid mechanics to write velocity or acceleration. One is a Lagrangian description, and the second is a Eulerian description. Lagrangian description. And the other one is Eulerian. Lagrangian description is what I just mentioned. Okay, so I'm looking at certain a fluid particle, and then I'm just looking at where this fluid particle moves. Okay. And then I pick another particle, then I follow fluid particle B. But there are too many, right? Infinite number of particles to follow. So it's very natural to use Lagrangian description, because that's what we are interested in. But it's really difficult, or almost it's impossible to follow all the fluid particles. Okay. So although the Lagrangian description is natural, and but in practice we will use Eulerian description. But anyway, so in Lagrangian description, fluid particle, you have to specify which fluid particle you will follow. So fluid particle A, and then that will be, it depends on time. Okay, so that's what the Lagrangian description is. Of course, you have to change the name of particle if you're interested in velocity of different fluid particle. And here, once again, this means there are three components. U, Okay. On the other hand, Lagrange description, Eulerian description, we don't care which fluid, the names of fluid particles. Okay, this is more like field description or field representation or description. It doesn't matter. Representation. So in this description, what I do is I just take a picture, snapshot. Okay, at a given time, I take a picture. Then I see, what velocity. So in three-dimensional space, I don't care who is who. Okay, I just take a picture. Then I draw if there is a way to do, I draw a velocity vector at a given point, x, y, z, and different point. This is the velocity vector, u. Even though I draw, the many arrows, each arrow corresponds to a different, fluid particle. So I'm not following, fluid particle, each fluid particle. I just take a picture, and I don't care, what the name is of this fluid particle sitting here. I just measure, the velocity, and then I draw arrows. So everywhere I can do that when I take a picture. If I have a special, camera which can, measure, velocity. By just clicking, the camera, I can, draw velocity field like this. So this is velocity field. Okay. But I didn't give name of each the position. Okay, the fluid particle is sitting on each position. So here I'm saying u to me is just function of x, y, z. That's a position of each dot. And also if I take a snapshot at a different time, then I'll get a different, velocity field. Is it clear? There is the experimental equipment called, PIV, which means, particle image, velocity meter. So there is a certain, the experimental equipment. By using that, you can do the, really take, the picture of velocity field. Okay. So in this case, I don't care which, what the name of this fluid particle, and so on. I'm interested in, what is the velocity at this point, and this point, and this point, and so on. Okay. Where it came from, I don't care. At a given time, I'm interested in, velocity at a certain, at any position. Okay. So by doing so, we don't have to follow each fluid particle. Okay. But in this case, u depends on not only time, but also x, y, z. So the functional dependence becomes more complicated. Here, the velocity depends on only time. Once you fix, the fluid particle, or once you, choose to follow a particular, particle, then it's a function of time. But here, since we don't follow fluid particle, the velocity depends on x, y, z, and t. Okay. So functional dependence is a little bit more complicated, but you can find by using that at a given time you can find a field of physical quantity. In this time, velocity could be acceleration or pressure. Okay. But this time, it's a vector field. Okay. Now we know what the velocity is, and then we need to define acceleration. You know what the acceleration is, right? Acceleration is time derivative of velocity. That's the acceleration. It's a simple. If you follow a particle, okay. So to get the acceleration of fluid particle A, what I need to do is take the time derivative of velocity of certain particle. By doing so, I can find the acceleration of that fluid particle. Correct? In physics, in freshman physics, you have done this. Once again, this is a vector, and therefore acceleration has x component, y component, and z components. But when you look at the representation of velocity of fluid particle A, it has a time dependence like this, and okay. Okay. But I want to use this Eulerian description to find u of this the UA. Okay. To do that, what I need to do is I follow particular particle This is nothing but what I call UAT, right? So this time I know where suppose I know where the fluid particle is going or is moving, x, y, z, and then I can find Lagrangian velocity by evaluating the Eulerian velocity at the positions of fluid particle A. Make sense? So given time, I know velocity everywhere. If I know where the particle A is at given time, I can get the velocity of fluid particle A by doing this. Right? No? Doesn't make any sense? I'm looking, okay, let's just say we have a 2D field. I know velocity everywhere. There are an infinite number of fluid particles. Suppose I know where the fluid particle A is. Okay? So I know where suppose I know that. Then since I know fluid field everywhere, it's easy to find velocity of fluid particle A but by just evaluating this U at this position. Okay? That's what I wrote here. And then, since time dependence appears here and here, I have to use a chain rule. I hope you know what the chain rule is. So I'm taking, time derivative of this guy, meaning that I fix, x, y, z. Okay, that's what it is. And then I have this, and then dxa dt. And then I have du dy and dya dt plus du dz dza dt. So the connection between these two velocities are given here. Okay. What is this? dxa dt. It's velocity of fluid particle in the x direction. So this is nothing but UA, and this is nothing but VA, and this is WA. U, V, W are the x, y, z components of velocity, and therefore I can rewrite this as du dt plus UA du dx. This is still vector, okay? And then VA du dy, and then WA du dz. That's the definition of acceleration of fluid particle. And in general, this is true for any fluid particle. It doesn't have to be true for particle A. It can be true for particle B by just replacing A by B, right? So therefore, I can drop, the A, and in general, acceleration is given by du dt plus u du dx plus v du dy plus w du dz. Okay. It's a long, expression, so we often use this way, and then we call this is a material derivative. So this is the definition, okay? Definition. And this derivative is called, material derivative. So it's a little different from, usual derivative. These are the usual derivatives, okay? And this is a material derivative. This is a shorthand notation, basically, to represent, this long expression. So you can take it, you can find the acceleration of fluid particle by just taking material derivative of Eulerian velocity field. That's what we got. Okay. Acceleration is specific to the fluid particle. That's why we take this derivative. But at the end, we can find acceleration of fluid particle by just taking material derivative of Eulerian velocity. Okay. So that's how we get the acceleration in terms of Eulerian velocity. As I said, this description is too much for us, so we are not going to use it, and we have to use, the Eulerian description, and then we have to know how to represent, acceleration in terms of Eulerian velocity. The reason is, sooner or later we are going to use, for example, Newton's law. Newton's law is nothing but mass times acceleration has to be balanced with the force acting on the particle, right? So we have to define acceleration, and that's why we need this kind of representation. So far so good. So one thing that I want to point out is the acceleration is not just the time derivative, partial time derivative of velocity, Eulerian velocity. If it is, the Lagrangian velocity, then of course you just take the time derivative because this guy only depends on time, right? But Eulerian, velocity in the Eulerian description depends on not only time but also space, x, y, and z. And because of that, when you get the acceleration, we have to take not only partial time derivative, but also we have to take partial the spatial derivative. Okay. Any questions so far? Too straightforward? At this point, I'm going to introduce steady and unsteady flow concept. I often say flow is steady or flow is unsteady. What I mean by that is when I take a time derivative, partial time derivative, okay, of something, could be velocity, acceleration, pressure, whatever. If this guy is equal to 0, then I say the flow is steady. Otherwise, if this guy is not equal to 0, then I say the flow is unsteady. Very simple concept. But once again, this is a time derivative, partial time derivative. So let's go back to this. If flow is steady, this term, based on this definition, is 0. But these guys don't have to be 0. Okay? So even though flow is steady, in other words, velocity field doesn't depend on explicitly on time, acceleration is not equal to 0 because these guys don't have to be 0. So going back to the Eulerian the picture, what I mean by here is I can draw a given time. I can draw a velocity vector, right? That's a velocity field representation in Eulerian description. So this is a given time t. Let's say t1. I can draw a velocity field. Based on this definition, velocity field doesn't depend on time explicitly. So at t equal to t1, I see this. What happens if I look at the same velocity field at time t equal to t2, which is different from t1? Do I get the same or not? Since the velocity field doesn't depend on time, I would see exactly the same velocity field. That's what I mean by steady flows. Okay? But that doesn't mean velocity at each position is the same. So the fluid at this point, the velocity at this point is different from velocity at this point in terms of length and in terms of direction as well. Okay. So, but suppose the same direction, this guy 1 and 2. So this is steady flow. In other words, if I see this side, and if I look at the flow field at t equal to t1, I see something, and then I see somewhere else for a while. I go back and I look at the same field, then I see exactly the same velocity field. That's what I mean by steady, because it doesn't depend on time. It doesn't matter when I look at the velocity field. I'll see exactly the same velocity field. But as I said, the velocity at different positions might be different. So there is a fluid particle, of course. I don't know the name of the fluid particle at this position 1. It came from somewhere. But fluid particle continuously moves. If fluid particle doesn't move, I don't have velocity, as I said. So fluid particle here keeps moving, and fluid particle reaches position 2, then it will have a different the velocity, right? That's what this the arrows imply. So if fluid particle is sitting here, then it has this velocity. If fluid particle moves somewhere, I don't know how they move, but if they reaches this position, then this guy has a different velocity. So what does that mean? Fluid particle has to accelerate or decelerate to have a different velocity, right? So if I move same speed, I don't have to accelerate or decelerate. But if I have to start to move, and then I have to move fast, I have to accelerate, okay? So even though flow field is steady, because I'm not really following a fluid particle, even though flow field is steady, there is acceleration of fluid particle. Because, at different locations, fluid velocities are different. So in each fluid particle has to accelerate or decelerate to get this velocity here. And if it goes here, then the speed is reduced. So fluid particle, I don't know how they move, okay? But to reach this position, they should have a smaller velocity, meaning that has been decelerated, okay? That's why I have these guys non-zero terms, even though this guy is identically 0. Might be confusing, but just think about it, okay? Later, when you have time, okay? But so the material derivative, to get the acceleration, not only you need this, but also extra terms which represents what I just described. Of course, if the velocity field changes in time, then of course there is a acceleration, local acceleration as well. Okay, but even though it is steady, we still have acceleration here. So for example, if your flow field looks like this, okay, it's independent of time, right? So du, dt, dv, dt are 0, but acceleration is not equal to 0. The reason is, if I take u du dx, what is it? X times 1, which is x, and v du dy, of course this guy is 0, but this guy is not, okay? And so you have a x component acceleration. Also you will have a y component acceleration as well, because of v dv dy and v du dy. No. This guy is 0, but this guy is y, minus y. So this is a component for ax, and this is component for ay, y component, x component. There are 3 components, right? So x components, you have this, and y component you have this. Okay. So the point is, even though we have a velocity field like this, there is fluid particles, accelerate and decelerate. Okay. Typical steady problem that we're going to look at later is, body moving with a constant speed. Okay? Or body sitting here and flow coming, uniform flow is coming toward, this body. Then this is a steady problem. Uniform flow is coming, and then the flow field wouldn't change in time. Okay. But if body is accelerating and decelerating like this as it moves, then it's a unsteady problem. Also, when you have waves, free surface is moving continuously in time, then that's an unsteady problem. Okay. But if this guy is sitting and if you have a uniform stream, then it's steady. Or if this guy is moving with a constant speed, this is in this frame is an unsteady problem because position of body changes in time, therefore flow field, velocity field will change in time. Okay? Even though this guy is moving with a constant speed, it's time dependent. Just look at this. This guy is moving. Close your eyes for a minute, for a second, and then open. This position has been changed. So this is definitely time dependent. But if you choose, reference frame, or if you move with this guy, then this guy is a steady. This problem is a steady problem. Okay. So this is Galilean transformation that we are going to talk about later. But anyway, for some problem, depending on the frame of reference that you choose, the flow can be steady or unsteady. But once the body starts to move with an acceleration, or then you cannot make the problem steady. But if the body is moving with a constant speed, then when you move with this guy, then to you this body is stationary. Okay, so then you can make it problem steady. I'll talk about that later. But at this point, all you need to know is the definition of steady and unsteady flows. Okay. So far, I talked about what the velocity is and what the acceleration is and so on. But I didn't tell you, I haven't told you how you get the velocity and acceleration. Okay. Of course, once you know velocity, you can get the acceleration by taking material derivative. But I haven't told you yet, how you get the velocity field. Okay. The answer is you have to solve some mathematical equations to find velocity field. Okay. And the question is what kind of mathematical equations you have to solve. So next, what I'm going to do is I'm going to show you how to derive mathematical equations that you need to solve to find the velocity field. Okay. To do that, we have to use certain physical conservation laws. Okay. And what we are going to do is we are going to look at conservation of mass and conservation of linear momentum. Those are the two things that we are going to look at in this course. In fluid mechanics, more general fluid mechanics, we have to look at conservation of energy as well. But in this course, temperature is not our main concern. Okay, we assume temperature doesn't change. or even though it changes and we don't care. Okay, but in some field of fluid mechanics, the temperature is a very important quantity. For example, if you're interested in heat transfer, and then you have to talk about the temperature and conservation of energy. Okay. Because for example, friction, if you rub your hands, you feel warm, right? So I put energy to move my hands, and some energy change into the heat, and then you have to talk about energy balance. But this time I don't care where my heat is. Okay, all I know is how much I have to how much energy I have to put to move my hands. Okay, that's basically my interest. Okay, but if I'm interested in how hard my hands will be, then I have to talk about conservation of energy. But this time we are only interested in mechanics, and therefore we'll talk about conservation of mass and conservation of linear momentum at this point. Okay. So to write conservation of linear momentum and conservation of mass and conservation of linear momentum, I need some mathematical theorem which some of you have seen in the last semester, which is the Reynolds transport theorem. Okay, so let me write down the Reynolds transport theorem, which is a very fundamental theorem for fluid mechanics. So often what we are interested in is time derivative of some physical quantity integrate over a fluid volume. Okay. This F can be the density, can be velocity, okay, or it can be density times velocity, and then we take the average over. We take the volume integral. So we see some volume here, which depends on time. So this capital V is a volume, okay, volume of fluid. But this volume, unfortunately, is moving in time. Instead of fixed volume, it is moving in time. Okay. If that is the case, then we have to take this time derivative. When we take a time derivative, there is a little difficulty because of this guy. Okay. If this guy is independent of time, all I have to do is just bring this guy into here and take a partial derivative. Okay. That's all I have to do. But because of this guy, since volume changes in time, I have to use certain theorem, which is Reynolds transport theorem. As a simple example, probably you see the Leibniz rule. This is a 1D version of this actually. So if you have a 1D integral of some function, this time it depends on only x, 1D. Okay, it depends on only x and t. This depends on x, y, and z, x, y, z, and t. So this underline means f depends on x, y, and z. Okay. But my integration limits depends on time. Then what do? Of course, you take the time derivative of this guy. Right? But that's not it. What do? We have to take a time derivative of this guy and this guy. So what we do is dx2 dt times f evaluated x2 minus dx1 dt times f x1 t. I hope you have seen this in your calculus class, right? So because of this x1 and x2 being time dependent, you have to take, you have to include, these two terms. Those are nothing but, boundary, okay? Or domain, so x1 is here, x2 is here, but they changes in time. So the length of domain changes. Because of that, you need this. So in fluid mechanics, you can define fluid volume that you want. But if you follow the same fluid particles move. So instead of having a same fluid volume, you could have fluid volume like this at a later time. So this could be volume, whole volume. This could be Vt plus delta T, right? So since volume can change in time, we have to worry about the effect of this guy, all right? Here? Oh, it has to be f of t. That's what you mean. No, it has to be x. That's what I wrote. Oh, it has to be dx, yeah. Sorry, yep. The integrand has to be x, yeah. Thank you. Okay, so on Thursday I'll continue, and I'm going to write the Reynolds transport theorem, and I'm going to apply this theorem for conservation of mass and conservation of momentum to derive, the equations for velocity and other physical quantities. Okay.